So first, let's talk about standard construction. It's one of the methods to construct the paths of Brownian motion process. And as you can see, we first let this Wt to be our Brownian motion process, and we are sampling this process at different time steps from 1 to d number of time steps. And we have this random vector of Brownian motion realizations. So W is normally distributed by the definition of Brownian motion, and it's going to have mean 0 and covariance matrix of C. So if we think about what are the covariances between two Brownian motions, so basically if we consider Brownian motion, let's say T and S, the covariance is given by the expectation of this W T times basically, well, we can subtract the mean, but the mean is 0 anyway, so that's going to be this expectation. But also notice that we can, so assuming that t is greater than s and greater than 0, so in this case we can add and subtract this. Sorry, this is t of, this is s, so we can write this as plus this square. But notice that this expectation of this, the first term here, that's going to be equal to 0, because we know that the Brownian motion increments, so this is from actually 0 to s, and this is from s to t. So these increments are independent, so their covariance is going to be equal to 0. So this term actually will vanish. And what we have is expectation of this ws square, which is going to be the variance of this term, which is equal to s. So we can see that actually the covariance of each couples in this form, of course we will consider different time steps here from t1 to t of d, but these covariances are going to be just simply the minimum of these two time steps as we have seen here. Okay, so this covariance matrix can be clearly written. So actually in the next slide we can see that. And this covariance matrix can be decomposed using the Cholesky decomposition. So that will give us this A. Okay. So again, going back, we are decomposing this covariance matrix C, which we know how to calculate. And the Cholesky decomposition will return us the upper or lower triangular matrix A. Okay. And basically using this A, our goal is to simulate these Brownian motion paths. So you can see that once we apply the Cholesky factorization, we will get this matrix here. And also if you do the multiplication with our, actually, so these are standard normals. Right? And our goal is basically to get this A, and if we multiply with the vector of these standard normals, so you can see that, for example, the first row, we will have square root of t1 times, we will have our z vector here. So it will be multiplied with the first standard normal we have. So it gives us actually a recursive formula. You can see that if you go to the second row, these terms will be multiplied with the first and the second standard normals. And the first term here corresponds to the previous WTI that we have simulated. So in the standard construction, actually what happens is we can start with the first Brownian motion term and then go to the next time step by adding the new random noise, basically multiplied with, this is coming from the standard normal times the square root of time difference, which captures the variance, right? So for example, if you take the expectation of this guy the expectation is going to be equal to simply the previous time step that we have. And the expected value of these zi's are always 0 because they are coming from standard normal distribution. And similarly, if you check the variance of this term, since this is a constant now, because at time ti, we already know the value of this wti, so that's just 0 for the variance. And the variance of this ci plus 1, that's always equal to 1 because it's standard normal. And you can see that the variance of wti plus 1 is simply equal to ti plus 1 minus ti, so which is as expected. Okay, so we can see that this method is gonna help us to simulate the Brownian motion paths, which we will do in using the Monte Carlo simulation. And we can also do this whole operation using just linear algebra. So once we obtained our matrix A, which is the lower triangular matrix from the Cholesky decomposition, we can simply multiply with the vector of standard normals that we generate, and then that's going to give us one path of the Brownian motion process. So obviously in a simulation we might want to simulate many paths of the Brownian motion. So this whole multiplication can be, this whole operation here can be repeated many times to get many paths of the Brownian motion process.